Okay, now we are moving to asphaltene. I suggest, or we can start asphaltene. And yeah, we can start asphaltene, then give you a break at some good point. So naphthalene, we know the role of naphthalene, paraffin, initiating wax formation. Naphthalene increase the amount of wax. Aromatic, they are good solvent. They are good solvent, but they are poison. So if you have high aromatic in your oil, you have to make sure that you protect yourself because they can cause cancer. They smell nice, but sometimes nice smelling material can cause problem. So polar component, the resin and asphaltene. Now we want to talk about asphaltene. Asphaltene particles are very big. They are very big. And they are already in colloidal stage. Basically, they are solid. But they are being kept in small colonies. And they are separated from each other with this compound, which is called resin. Okay, so they are very big component, molecular weight from 500 to 500,000. Okay, and they are very big and different test technique. The industry uses heptane titration, and that is one technician. But now we are sort of challenging this technique, and we have started a new wax asphaltene project, and start in a few days time. And we believe that we need to have a better understanding asphaltene and test technique. But in general, resin and asphaltene, they are keeping the fluid together. You see that here, this is asphaltene particle, okay? And these are resin particle. So another one asphaltene here, one is here, and this is the hydrocarbon, okay? Obviously, asphaltene particle want to have stick to each other, yeah. So we have some natural, this is liquid phase, natural surfactant, and so anything that increase the distance between asphaltene and resin can result in asphaltene formation. This is a theory that I developed in a way. Well, I say I developed because I haven't seen anywhere this is the idea that maybe somebody else has also developed, but it will explain all the process that can result in asphaltene deposition. Okay, when asphaltene can happen? One technique, one process that can result in asphaltene deposition is normal production. Normal production. Depletion. Yeah, depletion. So if you look at the depletion of a reservoir, And let's see, I have space here. Okay, so this is a blank page. You have, this is a temperature volume plot, pressure volume plot, pressure volume plot. And then when the reservoir pressure drop, the oil will expand, although it's not a lot, up to bubble point. At bubble point, gas appear. You change the slope up to the dew point. And below dew point, we have gas. Okay? So this is the bubble point. This is the dew point. And we can do this test at different temperature. It will be something like this. Okay? So we call this section is a single phase, oil. We call it depletion. You haven't reached to the asphalt, the bubble point. You see that here expanding. So when it's expanding, the distance between wax, asphaltene and resin is increased. So if you look at the oil volume versus pressure, this is volume, this is pressure. You see that the oil will expand up to bubble point. At bubble point, gas is released, the oil will shrink. So expand means that the distance between them will increase. And when the distance increases, then the attraction force between asphaltene and resin will be reduced. And therefore, asphaltene can form. At the moment, if you plot this pressure temperature diagram, temperature, this is a phase envelope, this is the bubble point, and for an oil reservoir, the temperature is below critical point. This is a critical point, yeah. And you see that as we are moving down here, it's like we are moving here. We are moving here. So the volume increases. So here we have asphaltene issues. This is asphaltene onset point. You see that above bubble point, start asphaltene forming. And then below bubble point, the gas is released. Gas is released. So this is the volume of gas. This is the volume of oil. So the oil will shrink. As the oil will shrink, the problem of asphaltene is reduced. And here, we don't have any asphaltene problem. Yeah, so that's the shape of asphaltene phase envelope. So depletion, you see that can result in asphaltene formation. Okay, so let's go for our coffee break for half an hour and come back. Any question?
Not actually, no, sir.
Okay, thank you very much. Enjoy. So what we are discussing is the various processes that can result in asphaltene formation and deposition. One of the processes that can result in asphaltene deposition is depletion. Yeah, that when we produce the oil, and so asphaltene is a function of pressure and temperature. You see that the shape of asphaltene curve, it will impact, the pressure will impact asphaltene formation, and the pressure, the temperature of the reservoir is here, for example, and as you produce, the pressure drop. So this is very bad news because asphaltene can form in the reservoir, and we don't have access to reservoir. Okay, and also it can form in the tubing and surface facility. So that's one process, depletion. The other process that can result in asphaltene formation is acid job. Yeah, when we inject acid. Why do we inject acid? To improve permeability. So acid, we have carbonate reservoir plus HCl, yeah, create. This is 2 HCl, create calcium carbonate plus H2CO3 carbonic acid. And this will be converted to CO2 plus water. CO2 will dissolve in the oil. CO2 will dissolve in the oil, and when it dissolves in the oil, it will increase the distance between resin and asphaltene, therefore asphaltene can deposit. So acid job can result in asphaltene deposition. EOR, enhanced oil recovery, is normally conducted by light gases or CO2. We inject CO2, CO2 dissolve in the oil, make the oil, volume of the oil more, increase the volume of the oil and reduce its viscosity. But again, this will dissolve in the oil, increase in the volume of oil, increase the distance between resin and asphaltene deposition will happen. Gas lift. We inject the gas to reduce the density of the oil in the column, but gas is light gas. Dissolved in the oil will result in asphaltene deposition. Blending, mixing two fluid. Yeah. One is light, one is heavy. Light component will dissolve in the oil and increase the distance between resin and asphaltene can deposit. And titration, that is C5 or C7 titration that we add to the asphaltene to the oil, increases the volume as oil, and therefore results in asphaltene deposition. The problem I found, to my opinion, I might be wrong, that a lot of companies, they use titration as the base test for modeling asphaltene. I don't think that's the right approach. I think you have to simulate the process itself. If it is depletion, we need to simulate depletion. If it is acid, we need to simulate that to get a correct representation of asphaltene. But the base is that, to my opinion, that increasing the light component will increase the distance between resin and asphaltene, resulting in asphaltene coming out of solution, and that will happen in depletion, that will happen in gas injection, acid treatment. So any process can result. Here you see that the titration, you see that with different titration component, C5, C6, C7, we normally use C7. And you see that the effect of titration, you see that with different volume of titration, normally we use 40 times. And therefore, we basically can measure there is a maximum amount of asphaltene that it shows the amount of asphaltene in the system. And we also, for detecting asphaltene formation, we use visual detection system and basically see the change in the level of detection. And therefore, if you have asphaltene particle, reduce the amount of light coming from the other end of the cell, and it's called solid detection system, yeah, SDS. There are various bases, and here I mentioned 40:1, yeah, for asphaltene measurement, and detecting asphaltene onset point. We can use gravimetric technique. We can use acoustic sound technique. We can use light scattering technique, and we can use other techniques, filtration. A problem, it is a serious problem, can happen in the reservoir and can happen in the pipeline and surface facility. In the past, a fluid either had asphaltene problem or not. But now, because of EOR, all the reservoir can have asphaltene problem. So something to consider if you are designing enhanced oil recovery. And that is, we discussed this before, because it can form in the reservoir, then asphaltene is a surface acting material, can change wettability, from water wet to oil wet. And that will reduce your overall recovery. So in the reservoir, that can be a serious problem. Here, effect of, and then in the reservoir, because the asphaltene or polar component are there. And if you have high drawdown and the moving of polar component creates electrostatic um, attraction, and that can result in asphaltene deposition in the reservoir, which will affect permeability. This is the upper asphaltene point. This is the bubble point. This is the bubble point, and this is the lower asphaltene onset point. The reason that asphaltene goes back to solution because above bubble point, you don't have, for example, reservoir pressure is here. You don't have asphaltene problem up to here. And then start asphaltene upper point. And then at bubble point is normally the maximum amount of asphaltene can form. Below bubble point, the light component will leave the system. So the heavier component gets close to each other and can dissolve the asphaltene back. Some people believe that you cannot dissolve all the asphaltene, and I would say that will depend on the time. And if you give enough time, maybe you can dissolve all of it. So this is a bubble point, the amount of asphaltene above bubble point 0, 2%, 3%, 2%, 1%, 0. Okay, this is a lower point. This is onset of asphaltene. This is bubble point, the maximum amount of asphaltene. And then below bubble point, light component come out, and therefore the heavy component gets closer to each other, and therefore asphaltene can go back to solution. We developed, as I mentioned, quartz crystal microbalance. Quartz crystal microbalance is a piezoelectric compound. Piezoelectric, I don't know if you have heard of piezoelectric compound. Piezoelectric are the compound that can create vibration with constant bit of voltage, or can create voltage with vibration. Yeah. For example, have you heard of some road in California, as you are driving, produce electricity? Have you heard of it? These are piezoelectric material. Yeah, piezoelectric material that when you drive on them, the load is reduced and increased. So you are changing the load that creates electricity. Our body creates electricity. How does it create? Our muscle. When we move, our muscle are piezoelectric material. When we move, that creates electricity. And we need for electricity for function of our body, and also each day we use billions of cells, and we have to regenerate that. And this movement and activity we have will help to rebuild the body, the cell that has died. Okay, and that's why you feel good when you do exercise, and for your health, the exercise is essential. Okay, so here the course is here, and we apply a voltage. As we apply voltage, it has a resonant frequency, and the resonant frequency is a function of density of the oil and viscosity of the oil and mass of the quartz. Okay, the mass of quartz. That is a stronger effect on the resonant frequency. So this is the front view. This is side view. So if the asphaltene deposit or wax deposit or scale deposit, then that will change the resonance frequency, reduce the resonance frequency. And because we can measure 1 hertz, so we can measure 1 nanogram, 10 to power minus 9. 10 to power minus 9 gram. That's why we call it microbalance. This is a balance, but it is microbalance. It's very accurate. It's very accurate. And this is onset point by the titration, by using QCM for detecting change in frequency. Yeah, this is the maximum amount of asphaltene, and then here max the asphaltene. When you add more heptane, asphaltene is the frequency is reduced. We have developed a setup that can go to 1500 psi, 1000 bar, and this is the basic of the QCM. We have another one developed recently that can go to 45,000 psi, 3000 bar. And this is the result from depressurization. This is the original crystal. This is in the cell. And this is the result after forming asphaltene. And you see that the frequency is dropping because change in density and viscosity, and then suddenly changes. That is asphaltene deposition. So starting from 15,000 psi, and you see that asphaltene deposition around 8,000, 8,500. Yeah, beautiful, isn't it? And this is testing different inhibitor, and very interestingly, if you have too much inhibitor, it will work against. So you see that if you have blank test without inhibitor, yeah, the blue line. Test 2. So they are relatively repeatable, okay? If you use 25 ppm inhibitor, you see that deposition is reduced. 50 is a bit more. 75, a bit more. So the best one is 25, okay? If you use 100, would be here. If you use 500, deposition is more. Yeah? So sometimes the inhibitor can increase asphaltene problem. And as I mentioned, you can have asphaltene problem with the reservoir, tubing, the flow conduits and surface flow line. And these are the causes: pressure drop, composition change, it reduces permeability, productivity loss, and primary depletion, enhanced oil recovery, acid injection, heavy oil extraction, well treatment, acetizing, and it will result deposition of the rock surface, pore plugging, wettability alteration, and emulsion formation, because they are like soap. They are like soap, surface acting material.